Hello there guys, and welcome back to another epic and inexorable maths video. In this video we're going to find the radius and interval of convergence of sine, and that's going to be centered at the origin. So we're looking at the Maclaurin series of f of x equals sine x. Okay, so let's write this down. So I'm saying that I've got sine x. I want to know for which values of x is the Maclaurin series, or the Taylor series centered at 0, you could say, of sine convergent. Okay, so this is the second video that we're doing on the radius and interval of convergence. So please check out the first video, link in description. But we're going to assume that you know what the ratio test is. We're going to assume that you know what Taylor series and Maclaurin series are, etc., etc. So one way, I used r in the last one, I'm going to use n here. I'm going to go that sine x is equal to the sum from n equals 0 to infinity. Again, this is centered at the value 0. And what do we have? Well, we know that sine, the Taylor series for sine x is x minus x cubed over 3 factorial plus x to the power of 5 over 5 factorial, and this just goes on and on and on. So what's happening? Well, we have the odd powers of x, so we're going to need an x to the power of, and it's going to be a 2n plus 1 there, and we're going to be dividing by the odd factorials, so 2n plus 1 factorial, and we're going to have the minus 1 there as well, minus 1 to the power of, is it going to be n or is it going to be n plus 1? Well, minus 1 to the 0 is positive 1, so it's going to be that way around. So that's how we can kind of build the sigma notation version of that, just you know, so that we can have it and stuff. And yeah, now we're going to take a little look at how are we going to do it? How are we going to find the radius of convergence? So let's have a look. We're going to need to use the ratio test again. The ratio test is always your best bet with doing these, okay? I guess there's definitely going to be situations where another test is better, but the ratio test is going to do us very nicely today. So we're going to take the limit as, and this time it's going to be n because I've chosen the letter n, as n goes to infinity of the ratio between the n plus 1th term and the nth term. So I've got x to the power of, and we have to be a bit careful here, 2 times n plus 1 plus 1 divided by 2 times n plus 1 factorial times minus 1 to the power of n plus 1, and all of that, very complicated looking fraction, but we're fine. We're big boys, we can do it. Divided by the nth term, so x to the 2n plus 1 divided by 2n plus 1 factorial. And hey, can't forget the big girls either. Don't think I forgot about you. Okay, and listen, we need this thing. I know it looks like a car crash, but we need this to converge. And the ratio test says that the series will converge if this ratio is less than 1. And of course, we have the absolute value there as well, because that's going to help us. Now, we've got a bunch of minus 1 business going on, but we're taking the absolute value. And as you probably know, when you take the absolute value of a negative number, it just makes it positive. So we can delete the minus 1 business. We don't care about that at all. But we'll do that in a second. So we have the limit as n goes to infinity here of the absolute value of, what have we got? So let's simplify. We have x to the power of, this is 2n plus 2 plus 1. So it's going to be 2n plus 3 divided by, and again this is going to be 2n plus 3 factorial. And again, I'm going to ignore that minus 1 because it's in the absolute value, so it's irrelevant. And I'm going to be dividing this by the same thing again. X to the power of 2n plus 1 divided by 2n plus 1 factorial, once again ignoring the minus 1 to the power of n. And I need this guy to be less than 1 still. Okay, so we're just working our way through the algebra, I guess, the algebra. Simplifying as we go, as always. The limit as n goes to infinity of, what have we got? So x to the 2n plus 3 divided by x to the 2n plus 1, that's just going to be x to the power of 2. So x to the power of 2 there. And what else have we got? I'm going to do this now. I'm going to bring up the 2n plus 1 factorial from the very, very bottom. Okay, you need to know about how to rearrange these really complicated looking fractions, okay? That's just algebra. I can't help you there. You just need to practice your algebra. Okay. here we are. And let's just have a little look, make sure we've done that right. I think we have. Lovely stuff, lovely stuff. Okay. And we're going to go limits as n goes to infinity again. We're almost there, guys. We're almost there. Now, again, we can do the oldest trick in the book, which is to rewrite the factorial business as follows. Okay, so numerator stays the same. Denominator, I'm going to write this as 2n plus 3 times 2n plus 2 times 2n plus 1. And I would keep going, but I'm just going to roll them all up by putting a factorial right there. Okay, and why have I done that? Well, as in the last video as well, we can cancel these guys out because they're the same number. Okay, we keep going. We have the limit as n approaches infinity of x squared divided by 2n plus 3 times 2n plus 2. And this needs to be less than 1. Now, guys, once again, let's look at this. Is there a single value of x that would make this not true? Well, no. Because no matter how big the value of x you choose, as n goes to infinity, we're dividing it by 2n plus 3 times 2n plus 2, and eventually that is going to get bigger and bigger and bigger to the point where the fraction is just 0. Okay, so in the limit, the thing inside of this will always be 0, completely regardless of what x squared is. X squared is a constant. It's a number that you would choose later. It's irrelevant what it is. This thing is 0 for any value of x. So it doesn't matter which value of x you choose. You are safe to choose any value. So this is true for, again, I'm going to say just in the last video, all values of x in the real numbers. But I have to emphasize that this is also true for complex numbers as well. Imaginary and complex numbers. So what can we say about the radius of convergence and the interval of convergence? Well, just like with e to the x in the last video, the interval of convergence, okay, is just going to be that x is between minus infinity and positive infinity. The radius of convergence, is a number, it's not an interval, and we use the letter capital R, and R is equal to infinity. Okay. Once again, as in the previous video, why do we have the word radius? What's the deal with radius? If you imagine the complex plane, okay, this is the real axis, this is the imaginary axis. Imagine a circle where anything inside the circle, I know it's a pretty bad circle, it's pretty bad, but anything inside the circle, the series converges, anything outside it diverges, so it's a radius. It really is related to a circle, but we just deal with complex numbers. If you don't want to mess with complex numbers, then you don't have to mess with complex numbers, okay? But actually, this is true for even complex numbers, because do you see, hopefully it makes sense, that even a complex number squared divided by 2n plus 3 divided by 2n plus 2 is still, in the limit as n goes to infinity, is still going to be smaller than 1. So there is no value, even a complex number like a billion plus 2 billion I or something like that, it's going to converge. So once again, this is really, really useful because we know that sine x, the Maclaurin series for sine x, is well and truly valid for any value of x that you choose, even complex numbers, but as big as you want. It's not like a geometric series where if you choose the common ratio to be bigger than 1, it doesn't diverge and it's meaningless. It's not like that. Any value of x will make this thing converge. It will converge for any value, even though it's an infinite series. So that's pretty cool. And I guess it's just because, simply put, the factorials are so dominant. They get big so quickly, and you're dividing by them, so it converges. The factorials, 2n plus 1 factorial, grows faster than x to the power of 2n plus 1. So that's the idea. So guys, thank you so much for watching. I highly appreciate it. As always, please let me know in the comments below whether there's anything I can do better, worse, or anything else, and I'll see you in the next one. Cheers.